to the course on medical biomaterials. We will continue on these metals, that is the metallic biomaterials. We have been talking about metals, their advantages and so on yesterday. We will continue on that. So, metals, they are able to carry maximum amount of load when compared to say polymers or ceramics. So, wherever you have load bearing applications like joints, like foot, leg, metals are very good. Ease of fabrication, the metals have been in use for several thousands of years. So, ease of fabrication is there. You can make very simple or we can make very complex shapes. Okay. There are several fabrication techniques, things like casting, forging, machining and so on actually. Okay. Good fracture resistance, they have good very good electrical conductivity, especially if you are talking about lead wires. Gold is quite commonly used, they can be formed into any shape. They are used predominantly in orthopedic and dentistry, cardiovascular devices like artificial heart valves, blood conduits, heart assist devices, vascular stents, and also in neurovascular implants. I showed you some pictures. For example, if you look at these are titanium cages you made up of pure titanium. Okay, so these are used in segmental bone defects. Okay, so they have less weight when compared to solid piece. So you can fill it up with allografts. Allograft is from the same patient bone fillings. Okay, and then they are placed here. This type of approach is adapted if the gap between the bone is too much. Okay, that is called a long segment bone. We will talk about that later. So, titanium is widely used, stainless steel bone plates, titanium bone plates, as you can see in these pictures. Okay, titanium bone plates or stainless steel bone plates are used, and they are connected to the broken bone using nails here, okay, as you can see in this X-ray picture. Okay, so bone, orthopedic is one big area where metals are used. So, we need to little bit understand this called the bone. It is a dynamic and highly vascularized tissue and it keeps to continue remodel throughout the life. That means bone can grow throughout the life, they can get remodeled. Okay. They are involved quite a lot in locomotion. That means when you move your foot and leg and arms and rotate your arms, they take in lot of load. They are able to, as you can see some of the weightlifters in Olympics, they are able to carry several times their body weight. They protect the internal organ like your heart, lungs, they are all protected by these bones. They are involved in hemostasis, that means they store calcium, potassium ions and they get liberated from time to time for the bodily functions. So, but then fractures are a very big concern. Orthopedic injuries, it is called, it happens because accidents, sports, age related, young people. So, all these happen, so bones break. So, that is a very big issue, orthopedic injuries. Fractures due to trauma related injuries account for more than 1.3 million procedures in US alone. Then can you imagine if you take the global, it could be about 50 times more than this, that is a big number. The total medical cost 215 billion per year with 8 lakhs bone grafting procedures. Okay. So, again you can see it is a big business, the medical cost. So, orthopedic injuries, bone fractures, replacement, filling up of bones, grafting. So, that is a very large chunk of medical cost. And again age, as the population, like some of the western countries, the population slowly aging, so age related injuries, osteoporosis, injuries because of frequent falls. So, all these can lead to orthopedic implant or orthopedic surgeries. Okay. So, what is this long bone segmental defect? Okay. So, a long bone, a section of long bone is completely traumatized or absent. This can happen because of congenital disease, from birth, or this can happen because there has been an injury and it is not possible to fix that portion, so there is a big gap. It can happen because there is an inflammation, infection, so the part of the bone has to be removed, or cancerous bone that has to be removed, so it needs to be filled up. So anything above 5 centimeter is called critical segmental bone defect. So the body cannot heal by itself. So if the gap is smaller than this, of course the bones can grow and they can fill up, but then if it is larger, what do we do? So we need to involve by a lot of biomaterials. So it needs specialized reconstruction, as it is called. Okay. So what are the main causes? High energy trauma, okay, accidents, revision surgery or removal of tumor, osteomyelitis, blast related injuries, developmental deformities, that means because congenital. All these lead to this long bone segmental defect, that is defect in the bone, gap in the bone which is longer than 5 centimeter. Okay, so how do they do it now? Vascularized fibular grafting. So they graft it, okay, in between. Distraction osteogenesis or internal bone transport with an external fixator. What do? They will externally pull the bones and then allow those extended portion to grow and so on. They keep on doing that, and it may take about 6 to 7 months for the bone to grow. So they use an external fixator and keep doing. That is a very difficult surgery, and sometimes both the bones may grow, but they may not exactly meet, then again there are problems. Okay. Another approach, using an intramedullary nail. So there is a long nail which runs through the bone from one end to another, okay, and then the remaining portion may be filled up. Cylindrical mesh technique. Okay. That means they keep a mesh, cylindrical mesh, filling up the gap. They may fill it up with the allograft as I showed you, or they may fill it up with the hydroxyapatite, calcium sulfate and so on, so that the gap gets filled, bone starts growing actually. So these are some approach here actually. So what are the properties, material properties the biomaterials should possess if they have to work in the area of bone? Okay. So mechanical stability, of course that is the most important, because bone is taking up a lot of load. Okay. It should match the elastic modulus and ultimate compression strength of natural bone. Otherwise if they do not match, if it is too much, then there is something called stress shielding. Okay. So they have to match. Stainless steel of course does not match, as I been telling you before. Titanium and newer versions of titanium are slowly, the elastic modulus keeps going down and down, so that they come closer to the values of the bone. Okay. Architecture, they have to mimic the architecture of the natural bone. Okay. They have to exactly look like the natural bone, porosities and so on, shape and size and so on. Biodegradability, so it will be very nice, you keep this biomaterial once the bone has formed, okay, and it completely disappears. So it should match exactly, the biodegradability should be exactly equal to the rate at which the bone is growing. Okay. That is called biodegradability matching. Next is porosity. Okay. You need to have lot of pores, and they should be interconnected, because we are talking about the blood flow and so many things, ion flow. So porosity should be around 70 to 95%, diameter of the pore should be 200 to 900 micron, and they ought to be interconnected so that the tissues can grow nicely, and that is very, very important. Next, biocompatibility, of course they should not produce any adverse, this is natural, any biomaterial, so they should not produce any adverse reaction to the host organism. We have talked quite a lot about it, biocompatibility. Osteoinductivity, what is this osteoinductive? Okay. Osteo, as you know, is related to bone, so it should promote stem cell differentiation through release of local growth factors. Okay. So it should allow the local cells to grow. Okay. So that means it should be able to release the local growth factors. Maybe if you coat the surfaces so that they release the factors, then that is called osteoinductive. Osteogenicity, so it should be able to produce new bone in the presence of osteoprogenitor cells. Okay. That is called osteogenicity. So it should produce new bone in the it should allow you to produce new bone, and at the same time it should be able to release growth factors for the bone growth. Okay. Osteoconductivity, okay, it should promote cellular attachment, migration, proliferation, because once you have the bone cell getting formed, there could be migration, there will be attachment one with an, and then there will be proliferation. So, that should also be happening. Promote vasculogenesis, this means we need to allow growth of new vasculature, that means we need to allow it for new blood vessels to grow, go through in and complete the architecture of the bone. So, a lot of requirements, okay, for the material, biomaterial, if it has to be used for bone application. Please note we have introduced some new terms here: osteoinductivity, osteogenicity, osteoconductivity. What is this osteoconductivity? It should promote cellular attachment, migration, proliferation, that means cells should nicely attach, proliferate and migrate. Osteogenicity, it should produce new bone in the presence of the progenitor cells. What is osteoinductivity? It should help in the differentiation, cell differentiation through release of some growth factors locally. So, all these are important: the osteoinductivity, osteogenicity, osteoconductivity, and then of course, it should allow blood vessels to form and penetrate through the pores, so that finally there is a good interconnection of the blood vessels. Okay, that is also very important. So, we have the mechanical properties, here and here, biological properties here and here, and then all properties related to the osteoinductivity, genicity and conductivity. So, it is quite a big challenge to develop materials for bone replacement. So, if we are talking about bone replacement, there should be many criteria: appropriate tissue material interface. This is like a normal biomaterial requirement. It should be non-toxic, of course, it should be non-corrosive, we do not want corrosion to happen, but that is a problem because when we use metals and when we are talking about stainless steel can corrode. Adequate fatigue life, okay. It should, because when we are talking about a joint, it is flexing all the time. So, it should be able to have good fatigue life, that is very important. Proper design, of course, density is very important, it should be of course relatively inexpensive, and then the elastic and mechanical properties comparable to that of the bone, that is very important. Okay. I have showed you these pictures, the cylindrical titanium cage, it is used nowadays quite a lot, especially when we are talking about long bone segmental defect, that is greater than 5 centimeter defect. The beauty of it is this is a cage, so it is lightweight, it is titanium. Titanium has a lot of biocompatible and osteo integration properties. So, one can fill this up with calcium sulphate or hydroxyapatite or allografts of the host, and then fill up the defective region. Okay. So, titanium and titanium alloys, orthopedic and dental, good mechanical properties, high corrosion resistance, they do not corrode like stainless steel, excellent biocompatible, and this is approved by the US FDA. Okay. And from almost the year 1999, these type of long bone segmental defects are being addressed using this approach. Okay. So, it is an hollow fenestrated nature, and it also able to take in the weight load of the individual and gives you the immediate limb stability. Okay. That is the advantage of this type of cylindrical titanium cage. And nowadays there is even talk about can we use magnesium, because magnesium cylinders they are bioresorbable, that means ultimately they can completely disappear, whereas titanium will stay in the body. So, magnesium, whether it can be used is being looked at. There are some research papers which talk about use of magnesium for long segmental bone defects. Now, hip again, metallic biomaterials are used in this area. Okay. Why? Arthritis majority, fracture, dislocation, rheumatoid arthritis, aseptic bone necrosis, that means there are infections in the hip and there is death, then revision, that is from the previous operation. So, if you look here, again huge data, 1 million hip replacements and 250,000 knee replacements are carried out per year. Okay. This is US data, that is a big number. So, use of biomaterials, metallic biomaterials in this area also again plays a very important role. Okay. So, there are many requirement, it should have long fatigue life. Okay. If it does not have, of course, it is going to have mechanical failure. So, one needs to do revision surgery, which is very painful, time consuming, expensive, success rate goes down. Adequate strength, that means if it is not taken, there could be implant failure, pain to the patient, and revision surgery. So, modulus should be equal to that of the bone, that is a very important point, and that is why new designs of titaniums are coming up, so that the modulus of metal is not affecting the modulus of the bone. Otherwise, if the modulus is very high, it is going to have stress shielding effects come into picture, loosening can happen, failure, revision surgery will happen actually, because the bone does not take in the load, where because the metal takes in the load which has got higher modulus. So, the bone becomes loosened. High wear resistance, okay. If there is a lot of joints wearing, implant loosening, inflammatory response, destruction of the healthy bone. Okay, the healthy bone also starts wearing because of this. Okay. It produces debris which can go to the blood, and if a person has a toxicity relates to say metal, chromium or nickel, then he or she is going to end up having other acute problems. High corrosion resistance. So, releasing non-compatible metallic ions and allergic reactions. So, if the corrosion resistance is low, it starts giving out a lot of unwanted biocompatibility. So, if not fulfilled, there could be adverse reaction in the system, or osseointegration. Okay. Otherwise, what happens if that does not happen, fibrous tissue between the bone and the implant, that means if there is no integration between the metal and the bone, and there could be gap. So, there could be tissues formed, poor integration of the bone and implant loosening. So, if the integration is not good, there could be implant loosening. So, as I said, the total knee replacement, we are talking in terms of 250,000 persons in US getting knee replacement. Okay. So, these knees, artificial knees contain 3 different parts, and we have metals, we have polymers like polyethylene. Okay. One is the femoral component. So, you can see cobalt, chromium, molybdenum, titanium alloys are used here. Okay. That is the femoral component. So, it is fitted. So, you also have some using polymethyl methacrylate fixing. Then we have the patellar component. So, femoral component, patellar component. Here polyethylene, cobalt, chromium, molybdenum. So, this cobalt, chromium, molybdenum is coated with polyethylene to reduce the wear resistance. Okay. Otherwise, there will be metal on metal. So, there could be lot of wear and debris could be released. So, that is why they coat with polyethylene. Okay. So, they fix again using PMMA, because PMMA, after all, PMMA is used quite a lot in dental application. It acts as adhesive. Then you have the tibial component. Okay. So, we have materials cobalt, chromium, molybdenum, titanium alloy. Again, it is fixed using PMMA. You see. So, 3 components. Okay. there are 3 components here, and you are using cobalt, chromium, molybdenum, titanium, and then in here you are using polyethylene as a coating, okay, or interface, so that it prevents the metal on metal rubbing, it improves the wear resistance. Okay. So, this is how the total knee replacement biomaterials are used, and predominantly you can see cobalt, chromium, molybdenum, and PMMA is used as a fixating to both sides on both the bones, where and you have the knee coming in between. Okay. Okay, so it looks very complicated. What happens to various metallic biomaterials in long term use in body? Okay. So, this was adapted from this particular reference, okay, trends in biomaterial artificial organs. We have stainless steel, we have chromium cobalt alloys, titanium alloy, nickel titanium, porous nickel titanium. Okay. Stainless steel corrosion resistance is poor, chromium cobalt also is poor, whereas titanium is highly non corroding, whereas nickel also can have corrosion problems. High elastic modulus, again stainless steel has very high, chromium cobalt has high elastic modulus, titanium has a problem, inadequate wear resistance, stainless steel also has inadequate wear resistance. So, that is why chromium cobalts are used in the knee region. Okay. And if you take nickel titanium, inadequate contact with the bone and surrounding tissue. So, osseointegration does not happen here. So, if you have inadequate corrosion, so there is going to be release of metallic ions. So, reduction in implant life, toxic effect or inflammatory response, because you are releasing metallic ions. So, high elastic modulus, you are going to have high stress shielding. So, there is going to be loosening of the bone. Okay. If there is going to be high wear resistance, debris are produced, corrosion by friction is going to happen. Again, this can lead to device failure, this can lead to inflammation, this can lead to loosening. Okay. So, if the inadequate contact with the bone and surrounding tissues, they are going to form fibrous tissues in between the gap. Okay. So, again there is going to be loosening, because you do not have a good osseointegration. So, all these can lead to revision surgery. This is a very interesting picture. So, we see titanium, the main problem of titanium is inadequate wear resistance. Okay. So, they could produce some debris and corrosions and toxic effect. Otherwise, stainless steel has quite a lot of disadvantages, and chromium cobalt also has some disadvantages, although they are very good wear resistance. The elastic modulus is high, corrosion effects are also high. Okay. So, some of them have good advantages, but there are some bad, there are disadvantages also. So, it is like a challenge in selecting or balancing between the advantages and disadvantages of various materials. Okay. So, what do they do? Porous coatings, because you need to have good pores, okay, so that the tissues, the vascularization can happen. They are using bioactive ceramics. These ceramics improve the osseointegration. Even bulk metallic glasses are being used. Okay. These inorganic material, they are highly biocompatible, non-toxic, and they are bioactive. So, they allow the integration of the material with the bone. But one problem of some of the ceramics is they can lead to infection. Tissue engineering approach, can I develop these tissues outside and brought inside, so that can I grow the bone cells outside and then bring it and grow inside. Of course, infection and other contamination issues needs to be talked about actually. So, if you look at the research, current research, especially in bone osteointegration, okay, and these are some areas very good for research purposes. Okay. Okay. So, we have metals, we have the polymers, we will talk about polymers later, we have the ceramics. Okay. These are properties you are looking at: hardness, elastic modulus, temperature strength, thermal expansion, ductility, corrosion resistance, resistance to wear, electrical conductivity, density, thermal conductivity. Some of them are very high, high, low, low, high, high, okay, both low or high. We can also have very low. Okay. So, if you look at metals, they have low hardness, high elastic modulus, okay, high temperature, low temperature strength, they have high thermal expansion, high ductility, they have low corrosion resistance, they have low resistance to wear, they have high electrical conductivity, high density, high thermal conductivity. Okay. So, the metals have these properties, okay, and polymers have different and ceramics are different. As you can see, at sometimes we need to have a mix and match type of approach, or coating of non-metals on top of metals to achieve the desired property. Okay. So, that is how we need to do actually. Okay. So, if you are interested in elastic modulus, okay, if you want very high, then we may go to ceramics or even high metals, okay, but polymers have much lower elastic modulus. If you do not want any thermal expansion, then of course ceramics are very good because they are low. Okay. If you want complete corrosion resistance, of course ceramics are the best. Resistance to wear also is best. Okay. Density, ceramics are low. So, obviously material size becomes very bulky. Okay. Polymers also low and very low. So, as you can see, we have different physico chemical properties, and you can have different grading of low, very low, high, very high, and so on actually. Okay. When you go to the mechanical properties, you remember this graph. Okay. So, metals, if especially when you draw a stress strain graph, we have the elastic region where, okay, the stress and strain are related in a linear fashion. Okay, here stress and strain are related in a linear fashion. Then here we have the heel strength, and this region is called the plastic region. So, this is the elastic region, okay, and this is the plastic region, and the slope is called the modulus. And finally, it breaks here. So, this is the ultimate strength, this is the yield strength, ultimate strength. Okay. For example, ceramics will not have a plastic region, polymers will have a lower modulus. So, it may go for polymers, graph may look like this. Okay. So, this region is called the elastic region, where the stress and strain are linearly related, if you remember long time back, and this is the plastic region. So, metals will nicely exhibit this type of graph, the stress strain diagram. Okay. So, again same metals, polymers, ceramics. So, ceramics of course do not have the plastic region, they have only the, okay, very small elastic region, modulus are very, very high, and as you can see, polymers have the lowest modulus, they are smallest toughness, large toughness, small toughness. Okay. So, this again, this picture you remember long time back, we have been comparing metals, polymers and ceramics in this fashion. Okay. So, different metals have different types of stress strain diagram. For example, stainless steel will look like this, nitinol, this is a titanium alloy, it will look like this, much lower, okay, and then it goes like this. Okay. Nitinol is a titanium alloy, it is used in cardiovascular stents, it has got many good properties. Okay. As you can see, the modulus is extremely low. Okay. So, metals can exhibit very large difference in this stress strain properties. That is the advantage of metals. We can have metals, metal alloys, so many different combinations, and then preparation method, and then there could be heat treatment method, by which one could change these stress strain properties dramatically. As you can see, stainless steel is very high. If you go to titanium, you may have one lower, and this particular alloy is much lower. So, wide range of variations could be achieved, as I said, metals and their alloys, preparation methods, and again heat treatment methods and so on. Whereas, if you take polymers, we cannot achieve these type of large differences in their stress strain behavior. Okay. So, again this is a very interesting picture. We will talk about this again. We have a lot of difference between the compressive strength and the elastic modulus. Okay. And let us not go into the ceramics part, we will talk about that later. But as you can see, the cortical bones have high elastic modulus and compressive strength. Okay. Cancellous bones have much lower. So, polymers are able to achieve some of these dense polymers, biodegradable polymers, and some of the bioactive ceramics could able to achieve. We will look at this diagram much later again once more. Again, this is also a very interesting picture. This was taken from this particular references called Biomaterials by Freeze casting. Okay. Nickel, chromium, stainless steel, they all come here. This is the fracture toughness versus Young's modulus. Fracture toughness is very important. So, if there is a crack that is developed in the material, how long does it last without completely breaking? That is called fracture toughness. Whereas, if you take, say for example, bones, cancellous bones, low density, high density, they have very low fracture toughness. Okay. Now, as soon as there is a fracture, it will immediately break. Whereas, as soon as there is a crack developed, they will immediately break. Whereas, if you take these nickel metals, even if there is a crack, they will not fracture for a very long time. That fracture toughness is very important. Okay. So, as I said, these bones have very low eggshell. Here comes dentin, that is the surface portion of your tooth, cortical bone, enamel, they have quite low fracture toughness. So, ceramic, calcium phosphate, silica, bioglass, okay, mercury amalgam, biosilicate. So, they all have much lower, zirconia. So, some of the inorganic materials are coming here, some of the bone and dental parts are coming here, and the metals are coming here. That is, they have very high fracture toughness, they have very high Young's modulus. So, if you take these inorganic material like bioglass, ceramic, they have very high Young's modulus, but their fracture toughness is quite low, as you can see here, right. So, they have very high Young's modulus, but their fracture toughness. So, if there is a small crack developed, immediately they can break, okay, just like your bones here, you know, as you can see. So, this is very interesting figure, I would say, which gives you a nice idea about fracture toughness versus Young's modulus. Young's modulus talks about the strength, fracture toughness talks about if there is a defect developed or a crack developed, how long, how tough the material is even with a defect like a crack. Okay. So, we will talk about these issues in the next class as well. Thank you very much for your time.